Let's review continuity conditions. If we want to prove that a function is continuous, the point has to exist on the graph. The limit has to exist. That means the graph has to approach the same y value from both sides. And then finally, the point has to sit where that limit exists. So, as a quick visual here, let's say this is point C. In order for a limit to exist, the point has to exist. The limit has to exist, so that means the graph has to approach the same y value from both sides. And finally, they have to be in agreement. The point exists at this value, and the limit also is approaching the same y value, so therefore we know the graph is continuous because all three conditions pass. Alright, so if we look at 13 here, these types of problems that involve piecewise functions and there's statements about continuity or limit, I think the easiest way is let's just step through continuity conditions. It gives us a structure that allows us to kind of see what things are in place and what's missing and where we are in terms of where our continuity condition falls. So we know that the x value in question is x equals 1. Since that's identified here. So our first condition is, what is f of 1? Right? F of 1, where's the point exist? F of 1 is at 4, so I'm going to just go ahead and identify that order pair. That's the first condition. Second condition, does the limit exist? So limit as x approaches 1, we know that this order pair 1, 4 is just a point. It's not a connected parts of graph, so if we're dealing with limit, we have to work with the portion that's a connected portion of the graph, which is this x squared minus 1 over x minus 1. This graph exists everywhere except x equals 1, so what that means is this is a connected part of the graph that we can determine the limit from. So limit as x approaches 1 of x squared minus 1 over x minus 1, we think back on our steps for algebraic limits, which is if we see a real number, let's plug that in. So if we plug that 1 in, we get 1 minus 1, which is 0. 0 over 0 is indeterminate form, which means that there is a whole that we can cancel out. If I factor the numerator, I get x minus 1. That matches with an x minus 1 in the denominator. I reevaluate the limit. I get a real number. I get 1 plus 1 is 2. So the order pair is sitting at a y value of 4. The limit is connecting to a different y value of 2. So that means the point doesn't exist where the limit exists. And if we were to sketch this out, we're going to see that there's a hole in the graph. The limit exists, but it's not continuous at x equals 1 because we have a removable discontinuity. And an example of what that could look like is it could be something like this, where we have order pair is at 1, 4. But the limit is at x equals 2. So visually we can see, obviously the graph is not continuous. The limit exists, the point exists, but the limit doesn't arrive at the same value as the point. So therefore not continuous. Number 14, again, it's a piecewise function, and there's statements about continuity. I'm just going to go ahead and step through continuity conditions. So the x value that's in question is x equals 2. So f of 2 is equal to k. That's just a statement that is identified with the second statement here. The limit as x approaches 2, the connected parts of graph is with this expression here. So I want to find the limit of that expression. If I try to plug 2 in, I get 0 over 0. That tells us that there's a hole in the graph. If I see radicals, I'm going to go through Conjugate Method, which means I'm going to take the numerator, I'm going to copy the numerator exactly. I'm just going to change the sign in between. So before it was radical minus radical, I'm going to multiply this by radical plus radical. But whatever I have up here, I'm going to copy the same term down here. Don't change the sign here. These are both going to be plus. I'm multiplying by 1, so I need to maintain that balance. So now what I can do is I can FOIL the numerator out. Okay, this is going to clean up nicely. Multiply these two together, I get 2x plus 5. The middle terms will drop out. And then the last terms, if I multiply the two radicals there, I get minus parentheses. Careful with the parentheses there. Minus parentheses x plus 7. If I distribute the negative through, I get 2x plus 5 minus x minus 7, which becomes just x minus 2. Denominator, I leave alone. Don't try to expand the denominator out, because this x minus 2 is going to be what we want to eventually cancel out. So leave the denominator alone. We just want to clean up the numerator. So if we leave the denominator alone, the x minus 2 stays visible, and we see that x minus 2 will eventually show up. We cancel those out. Remember, if everything cancels from the numerator, there's still a 1 left over. Reevaluate the limit. 2 times 2 is 4. 4 plus 5 is 9. We get square root of 9 there. We also get square root of 9 there. So root 9 is 3. 3 plus 3 is 6. So our limit is 1/6. So in order for the graph to be continuous, this k value, the point, has to be where the limit is. So if the graph is moving towards 1/6, we want the order pair to be at 1/6 as well in order to guarantee continuity. So therefore, k must be 1/6. Right, number 15, same thing, piecewise function. We step through continuity conditions. The x value in question is at 0, so f of 0 equals 1, based off the second statement. Limit as x approaches 0, the connected parts of graph is what we want to use for limit. So limit as x approaches 0 of our expression. If we plug 0 in, we get 0 over 0. If we factor the numerator, we get x parentheses x plus 1. Cancel the x's out, reevaluate the limit, we get 0 plus 1 is 1. So our order pair is at 1, our limit is at 1, there's a match. These are consistent, so therefore our third condition will also pass, meaning that the order pair does exist where the limit exists, and therefore it passes all of them. The order pair exists, limit exists, and the function is continuous. Okay, last page here. Number 16, we have a piecewise function where there could be issues at 1 and 2, and we have two separate values defined at 1 and 2. So if we want to test for continuity, we have to treat this like two separate problems. We have to check for continuity at x equals 1, and then separately we need to check for continuity at x equals 2. So for x equals 1, we know f of 1 is negative 3. That's the first condition, passes. The connected parts of graph is with this function here. It exists everywhere except 1 and 2, so we know it's a connected part of the graph that we can use for limit. So I'm going to evaluate the limit. I'm going to factor the numerator and denominator. X minus 1 cancels out. We reevaluate the limit. We get 3 times 1 was 3. 3 over negative 1 is negative 3. So the order pair is at 3. The graph is moving towards negative 3 as well. So there's a consistency. They match. We know there's going to be continuity at x equals 1. Third condition also passes. F of 1 equals the limit, which is equal to negative 3. Now at x equals 2, we're going to go through continuity conditions for x equals 2. So f of 2 equals 4, that's stated here in that statement. That's the first condition. Second condition, limit as x approaches 2, I'm going to factor just like how I did with the first go around. The x minus 1 still cancels out, but when I reevaluate the 2, I get 6 over 0, and 6 over 0 indicates that the limit doesn't exist. There's a vertical asymptote, and if there's a vertical asymptote, we know that the graph is not continuous. So therefore, our graph is continuous everywhere except at x equals 1. Sorry, except at x equals 2. And also, if you look at the factored form of our expression, we know that there's issues at these two values, right? X minus 1 is where there's a hole. X minus 2 indicates where there is a vertical asymptote, because this factor does not cancel out. For these next problems, we are just relying on the graph to help us with the limits here. So limit as x approaches 2, The limit x approaches 2, we see, okay, so I'm going to approach 2 from both sides. And if we approach 2 from both sides, we see that they're both leading us towards the same value. They're both leading us towards, even though it's a whole, they're both moving towards the same, in the same direction, towards the same y value. So there's a consistency there. The limit does exist at 0 as we approach 2 from both sides. Okay. For 33, the function is defined where? So from -1 to 3, we see there's a hole there, but that's defined at this y value. And anytime there's a hole, we see someplace else that's defining that y value. So we're not going to see, even though there's all these breaks along the point, there's no x value that is undefined between -1 and 3. 34, removable discontinuity. That means there's a hole in the graph, and the only hole that we see in the graph, that means the limit exists but not continuous. So the only place where there's a limit existing but not continuous is at x equals 2. On which of the following interval is the graph continuous? So the graph is continuous between 0 and 1, not including 0 and 1. All these others have places where we have endpoints that one of these endpoints being not continuous. 36, the function has a jump discontinuity. That means there's a non-removable discontinuity. What that means is the graph from one side is not the same as the graph from the other side. So that happens at 1. So as we approach 1 from the left side of 1, we see it's leading us towards a y value of 0. But if we approach 1 from the other side of 1, it's leading us towards a y value of 1. There's inconsistency there. They don't agree, so therefore we have a jump discontinuity or a non-removable discontinuity there.